Swayam Prabha. Digital India. Educated India.
In the previous lecture, we discussed about the solution of the single degree of freedom system subjected to ground excitation, and the single degree of freedom system was taken such that it goes into an inelastic range. The problem was that for a particular time station, the displacement, velocity, acceleration of the single degree freedom system were given, and for subsequent time station we are supposed to find out the displacement, velocity and acceleration of the system. The time steps were chosen such that there was a transition point when it was passing from one state to the other, and therefore all the theoretical background that were discussed when the state of the system moves from elastic to plastic, plastic to plastic and plastic to elastic, those state changes are explained with the help of that example. Now we take up the problem for a multi-degree of freedom system. This is the frame that is considered, and in this particular frame we have the different stiffnesses. For example, the bottom story has a stiffness of 1.5 K, the top story has a stiffness of 0.5 K, and the in between stories have a stiffness of K. The plastic shear capacity of the columns for the bottom column it is Vp3, for the top column it is Vp1 and Vp2, and these are the elastoplastic behavior of the column in shear. So, it is designated by a yield force in shear which is called Vp1, Vp2, Vp3 etc., and a yield displacement that is designated by xy1, xy2, xy3. The equation that we had discussed in the beginning, that was written for a multi-degree of freedom system, that is m delta x double dot plus c delta x dot plus k delta x is equal to minus m into delta x double dot g. So, in that the k is the k matrix, c is the c matrix and m is the m matrix. Now, depending upon the state of the system, the stiffness of the members are changed. The members which undergo yielding, for those members do not contribute to the overall stiffness matrix of the system, and K is set to 0 for them, and if the system is in the elastic or the member is in the elastic state, then the full value of the stiffness, that is K 1.5 K or 0.5 K for the columns that were shown, that are taken into consideration. Now, In order to solve the problem, we require iteration, as we have carried out in the case of single degree of freedom system. The solution for the multi-degree of freedom system is just an extension of the single degree of freedom system, and we have discussed how we developed the equation 6.11, that is k bar into delta x is equal to delta p using Newmark's beta method. Here k bar is a matrix instead of a simple one quantity that was there for single degree of freedom system, and delta p is also a vector, delta s is a vector. The k bar matrix is given in equation 6.12a, that is, it is consisting of kt, then ct and m. So, kt is the matrix which is the transition matrix or the stiffness matrix at time t. Ct similarly is a damping matrix, and M matrix is the mass matrix. In obtaining the Kt matrix, we take care of the yielding of the elements. If the elements, if an element has yielded, then for that, for construction of the Kt matrix, we set K to be is equal to 0. Similarly, delta P vector that consists of minus m r double delta x double dot g, where r is the coefficient vector, and these m is a matrix, ct is again matrix. So, whatever equation we had in the case of a single degree freedom system, they are m, c and k, they are replaced by the matrices m, c and k. Rest of the definitions of other parameters remain the same. Now, we explain how we go ahead for the problem which is shown in the figure 6.5. So, this is the problem that we are trying to solve. It is a 3-story frame having a stiffness of k by 2, k by 2, k by 2 for each column, and the Fy, the yield shear for the column is Fy, and Xy is the yield displacement. Fy is given as 0.15 mg, and where m is the mass of the system or this mass, and Xy, that is the yield displacement, is 0.01475 meter. Now, for this frame, we are trying to solve the problem at 3.54 second. We have to find out the responses given those at a time at 3.52 seconds. The quantities that are given is that Fk, that is at time 3.52 second, the forces, shear forces in the columns are 1.44, 0.95, 66, 0.6433. So, this is for the bottom column, this is for the middle column, this is for the top column, and all of them happens to be less than equal to the permissible yield shear for the column. Therefore, none of the columns has yielded. X dot is given as greater than 0. Therefore, it is in a elastic state, and it is increasing in the elastic state. The k bar matrix is given by this, and finding out the value of Kt, since none of the columns has yielded. Therefore, one can construct the K matrix, and this K matrix is given over here. It is not very clear, but this is the K matrix which is computed, and this is the M matrix which is computed, and the values of the displacement, velocity and acceleration at the time 3.52 seconds are given as these. Now, with the help of these values of the displacement, velocity and acceleration, the k bar matrix is determined using this equation, and the k bar matrix turned out to be this, and using these the value of delta x double dot g as 0.5913 and the R matrix as the identity matrix, that is a or a vector of 1 1 1, one can calculate this quantity, and then knowing the values of x double dot k, x dot k and x k, the values of delta p is calculated as this one, and once we get the value of delta p, then one can find out the displacement delta x as k bar inverse delta p, and that turns out to be this. Now, from the displacement, that is incremental displacement that is calculated, from that we find out the drift between the different floors, and the drift is given shown by delta x bar. The drift for the first floor is same as the displacement itself, 0.0032. The drift for the second floor will be the displacement of the second floor minus the displacement of the first floor. Similarly, the drift for the top floor will be the top displacement minus the displacement at the second floor. So, that gives us the drift, and the drift multiplied by the k by 2, that is the stiffness of the column, that gives the incremental force in each one of the columns. At kth time station Fk, the values were given. So, to that values delta f is added to find out Fk plus 1, that is for the current time station, and it is found that these value of the force, shear force in the bottom column, that exceeds the 0.15 mg, that is the yield shear. Therefore, the bottom column is yielding, whereas the other two columns, that is the middle column and the top columns, they remain in the elastic state. So, what is done is that we factor, as before what we discussed in this for single degree freedom system, factor the delta f in such a fashion so that the shear force in the bottom column, that becomes equal to 0.15 mg. So, we multiply these value of delta f by E1 by a factor of E1, then a factor of E2 for this, and a factor of E3 to the third column, and find out the values such that the yield shear remains less than equal to 0.15 mg. So, in that way we calculated the values of E1, E2 and E3, since the column 2 and 3, or the second floor column and the third floor column, they are in the elastic range, therefore, E2 and E3 are is equal to 1. Next, what we do is that once we know these values of E1, E2, E3, which are the scaling factors for the drift, that means drift is scaled. So, we wish to obtain now the scaling factor for the displacement, so that the displacements that we have got, that displacements are scaled such that the yield shear in the bottom column becomes just equal to the or the shear becomes equal to the yield shear for the first column. So, and that is what is called the first part of the displacement vector or the scale displacement vector delta xc, or what we are calling as delta x1, and this is written as that is E1 into delta x1, that is for the drift, whatever scaling factor is for the drift, the same scaling factor used for delta x1, and for the second column it will be E1 into delta x1 plus E2 into delta x2 minus delta x1, that is the drift multiplied by E2. So, that is what we have done over here, we know E2. So, similarly we can find out the displacement for the top floor, that is E1 delta x1 plus E2 into the drift plus E3 into the drift. That can be written as a revised scaling factor of E bar 1, E bar 2 and E bar 3 into delta x1, delta x2 and delta x3, and these can be worked out, what are the values of delta x1, delta x2 and delta x3, that is known to us because these quantities are known, delta x1, delta x2 etc. are known, E1, E2 etc. are known. So, this entire vector can be calculated and that is equal to this vector, and once you know this vector, from there one can find out the values of E bar 1, E bar 2 and E bar 3. So, these are the values of the scaling factors, and with the help of these scaling factors we get the value of the delta x1 or the scaled displacement. Now, next part is the once we have scaled the displacement to bring the bottom column forces within or equal to the yield shear, then we obtain the next part of the displacement, that is the plastic displacement part. So, this plastic displacement part delta x2, that is calculated using a revised stiffness matrix, and the revised stiffness matrix is given over here. You can see that in place of 200 now it is 100 and this remains equal to minus 100. So, the matrix is changed because of the yielding of the bottom column. So, you can see here the same thing in this figure, that once the bottom column is has yielded, then there will be no contribution, or the K value for that column would be equal to 0, and the force to produce a unit displacement at the level of x1, that will be equal to only K by 2 plus K by 2. From the bottom portion no contribution will come, and K by 2 plus K by 2 is equal to K, and that is equal to 100, and that is how we are getting over here the value of 100. So, the KT is revised. From this KT we get the value of K bar, and once we get the value of K bar, then we obtain K bar into delta x2 is equal to the 1 minus E bar 1, E bar 2, E bar 3 into delta p, this E bar 1, E bar 2 and E bar 3 that we have obtained before, that is the scaling factors. So, delta p vector is multiplied by these scaling to get the value of delta p, for which we will find out the plastic component of displacement, that is delta x2. So, once we get the value of delta x2, then we get the value of total displacement delta x. Delta x is equal to delta x1 plus delta x2. Delta x1 is the scaled displacement, and delta x2 is the displacement which is the coming due to the plastification part, or we call this as a plastic part of the displacement, this we call as the elastic part of the displacement, and once we add them together we get the total displacement delta x and vector, and delta x vector comes out to be this. Now, with this delta x vector, the xk plus 1, that is the displacement at the current time step, is obtained as sk plus delta x. Similarly, one can find out delta x dot knowing the value of delta x, and from these delta x dot is computed this way, and once we obtain the value of delta x dot, we can find out x dot k plus 1, that is the velocity at the current time station vector, and after we have obtained x dot x k plus 1, x dot k plus 1, then we try to find out the total force vector at the current time station. For that we get a delta f, and with the delta f, once we get the value of delta f, then we add delta f with fk to get the values of the fk plus 1. Now, the fk plus 1 is the yield shear, the shear at 3 floor levels, and for a particular column, and we can see that the bottom column, for that the shear is equal to the yield shear. For the other two, it remains less than the yield shear because they have not yielded. The 2 times this value is the total force. So, this fk plus 1 vector is 2 times this, because you have got 2 sets of columns in a particular floor. So, you use the equation of motion at k plus 1th station to find out the values of the acceleration vector. That is what we discussed, because if we find out the acceleration by satisfying the equilibrium equation, then the error that is introduced into the calculation that is compensated, and as a result of that there is no growth of error as the computation is carried over the time steps. Next we come to the bidirectional interaction. In the previous case, in the 2-dimensional frame, we had only one directional yielding, in the sense that in the direction of the earthquake, the entire frame, that is the plane frame, was undergoing a bending, and accordingly there was a yield shear, and whenever the column reaches the yield shear, it was assumed to be yielding. Now, in the case of bidirectional interaction, we consider the 2 component earthquake, or it could be a torsionally coupled system in which the columns will develop shear forces in 2 directions, that is x and y direction, and the yielding that takes place will be having an interaction between the 2 shears that are developed in the column. For such cases, elements undergo yielding depending upon the yield criteria that is used. So, whenever we have this kind of situation, that is yielding is due to more than one forces, then we have an yield criteria, and one can adopt different kinds of yield criteria. In the case of bidirectional interaction of forces, that is the forces developed in the x and y directions of the column, if we consider the yielding, then the 2 forces that are developed in the 2 directions, they are basically they are to be considered, and it is seen that individually in each direction the column may not reach the yield value, yet the section may yield because of the yield criteria that is assumed. Now, if the interaction is ignored, then the yielding in the two direction takes place independently, that is whenever the force in the x direction exceeds the yield shear in the x direction, or whenever the force in the y direction of the column exceeds the yield shear in that direction, then we say that the columns have yielded. So, they take place independently, but whenever we consider the interaction effect, then the yielding is considered based on certain yield criteria that is assumed. In the incremental analysis, the interaction effect is included in the following way that is explained over here. Say this is a frame in which you have got 4 columns. This is a one story frame. The center of mass is at the center. The columns 1, 2, 3 and 4, they have varying dimensions. As a result of that, center of resistance is such that there is a two-way eccentricity, Ex and Ey. The y and x directions are this. Now, the Ke matrix, that is the elastic stiffness matrix for the system, can be written as Kex, Key and K theta. Kex will be the sum of the stiffnesses of the columns in the x direction. Similarly, Key will be the sum of the stiffnesses of the columns in the y direction, and K theta will be equal to Kexi into Ey plus Key into Ex, summation for all the columns, and that is how one can find out this stiffness matrix for the entire system. The transient stiffness matrix Kt, which remains constant over the period delta t, for which we are writing down the incremental equation of motion. So, that Kt transient stiffness matrix is written as Ke minus Kp, that is the Kp is the modification factor. This modification factor is coming into picture because of the yielding of any element that can take place during the time marching scheme. So, at any interval of time delta t or in the beginning of that time interval delta t, the sum of the elements might have yielded, and for that we should account for the effect into the stiffness matrix of the system, and thus the Kt matrix is modified, and the modification is represented by this Kp matrix. Now, the elements of the Kp matrix that can be calculated using this formula. These formulas are proved in some of the papers and is available in many of the papers dealing with the plastification of the 3-dimensional frame system, in which bidirectional interaction comes into picture. Now, the Kpxi, Kpyi and Kpxyi and Kpyxi, they are given by these formulas, where Bxi and Byi are defined by this Kexi and Kyi multiplied by Hi and Hxi, where Hxi and Hyi are related to Vxi and Vpxi in this particular form. So, knowing Vxi, Vyy and the permissible yield shear for those columns, if they are known, then one can calculate Hxy and Hyi, and knowing the values of Key and Kexy, one can calculate Bxi and Byi, and once we know that, then Kpxi and Kpxyi etc. can be found out, where G basically I is given by this. Here again Hx I and Hyi, they are known, Kexi and Kyi are known. So, at any given state, knowing the values of Vxi and Vyi, one can calculate the components of the Kp matrix, and with the help of this Kp matrix, one can generate the Kp matrix itself and get the transient stiffness matrix of the system at any instant of time t. Now, if any column happens to have gone into the plastic state satisfying the yield criteria, then for that particular element we consider Kt to be equal to 0. Now, during the incremental solution, the Kt changes, that is for a particular element, the stiffness changes as the elements pass from elastic to plastic, plastic to plastic, or plastic to elastic, the way we discussed in the case of single degree of freedom system. When it is passing from elastic to plastic, then there is a transition point, and we should take care of that transition point into the solution, so that the displacement that takes place, the incremental displacement that takes place, consists of two parts. One is the scale displacement, we call that as the elastic displacement, and the another displacement part in which the Kt becomes equal to 0, and we get a plastic displacement. So, the scale displacement plus the plastic incremental displacement, that becomes equal to the total displacement. When the system changes from P to P, that it remains in the plastic state itself, then we check the yield condition that we will describe shortly, and whenever the system goes from plastic to elastic state, that means any element goes from a plastic state to elastic state, then we look into the plastic work done or the sign of the plastic work done. From that we decide about the transition point. The change follows EP properties of the element and the yield criteria. So, the elastoplastic properties must be given for all the elements, and the yield criteria is given by many kinds of equation. Here we take one of the very popular yield equation, which is given in this form: Vxi divided by Vpxi. Vxi is the shear in the column in the x direction for the ith column, and Vpxi is the plastic yield of the ith column in the x direction, or the yield shear of the column in the x direction. Similarly, Vyi and Vpyi can be defined, that is the quantities in the y direction, and the square of these two together is called phi I. Now, if Vpxi and Vpyi are the same, then the curve turns out to be a circular curve. If Vpxi is not equal to Vpyi, then the curve is an ellipse. Phi I is equal to 1, that is when the sum of these two quantities become equal to 1, then we say the plastification has taken place, or we say that it is the column is in the plastic state. Phi I less than 1 shows the column is in the elastic state, and phi I greater than 1 is inadmissible. And this is the check that we do basically when the system moves from one plastic state to other plastic state. That is, for each column we examine or trace what is the values of phi I, and if the phi I happens to be greater than 1 when it is moving from one plastic state to the other plastic state, then that is inadmissible, and in that case one has to pull down the forces. So, that is given the next step, that is, if phi I is greater than 1, the internal forces of the elements are pulled back to satisfy yield criteria. That means, we pull back the forces so that phi I becomes equal to 1. So, as a result of that, the equilibrium is disturbed the moment the forces are pulled back, and this the disturbance in the equilibrium is corrected by an iteration technique that will be described with the help of an example problem. The solution process otherwise is similar to that what we adopted for single degree of freedom system. At the beginning of the time, we check the states of the elements and accordingly obtain the transient stiffness matrix, and once we get the transient stiffness matrix, then we find out the solution for that and check the stresses in the elements, and if it violates the yield condition at the end of the time or passes from elastic to plastic, then an iteration is utilized to correct the state of the equation or to make sure that the yield condition is satisfied. Now, in the case when any column passes from plastic to plastic state, and if phi I is computed as greater than 1, then an average stiffness predictor corrector scheme is employed, and this scheme consists of finding out a tangent or the transient stiffness of the element, and this transient stiffness is an average transient stiffness consisting of the initial transient stiffness of the element, that is at the beginning of the time step, and k dash t is the transient stiffness at the end of the time step, and from this we work out an average, and that average transient stiffness is used for that particular column. In order to find out this k dash t, what is done, we make some guess in the beginning, and with the help of that we find out a kTA, and with that kTA we go ahead with the solution, and the solution gives a new value of displacements or incremental displacements, and from there one can calculate what is the revised value of the k dash t, that is at the end of the increment, what is the value of the transient stiffness for that element. So, now that one is used to calculate now kTA, and the process continues like that till some convergence is achieved. So, this convergence is examined for both the force in the column and the displacement in the total displacement in the system. So, the incremental displacements or incremental forces that we get, or that incremental displacement are examined in successive iterations, and between two successive values, or the difference between the two successive values, if they remain within some tolerance level, then we say that the convergence has occurred. Now, once the convergence is achieved, then the forces are calculated in the columns again, and the yield criteria for each one of the column is checked, and if it is found that phi I is greater than 1, then the element forces are pulled back, and this pulling back is done by this equation, that is the new force in the element, that is Fi dash is equal to the previous force Fi divided by the square root of phi I, and the say phi I here will be greater than 1 obviously. Whenever it is greater than 1, it is not admissible. So, therefore, we divide the force by root over phi I to get a revised value of the force. Now, with the new force vector, again we calculate the kTA is calculated and the iteration is continued. For the case when the column is passing from elastic state to plastic state, there is a transition point, then it is a straightforward extension of the single degree of freedom to multi degree of freedom system, that is we scale the displacement in such a fashion so that the yield condition is satisfied, and the total displacement consists of two parts. One is the scale displacement, other is the plastic part of the incremental displacement. So, we add these two to find out the total value of the delta x. If one or more element are unloaded from plastic to elastic state, then the plastic work increments for the elements are calculated, and if they are negative, that means those elements are unloaded and the plastic increment or work increment is given by this equation, that is Fi, that is the force in the element multiplied by incremental plastic displacement, and incremental plastic displacement is obtained like this, is equal to the total incremental displacement minus the elastic part of the displacement, that is KEI. It is simply the elastic stiffness matrix of the element into delta Fi. So, that is how we calculate delta UPI, and once we know that, one can find out these plastic work increment for that element. If it happens to be a negative quantity, then we say that the element is unloaded, and then for the calculation over that interval of time, we consider that element to be an elastic element, and the stiffness, elastic stiffness of that element is considered in constructing the overall stiffness of the structure. The method is explained with the help of a 3-dimensional frame, which is shown in this figure. This is a 3-dimensional frame having different columns with different stiffnesses. As a result of that, we have an eccentricity both in the x and y direction. The yield shear for the column A, that is given as 152.05 Newton, and by knowing the yield shear in column A, the yield shear for other columns can be obtained from this particular condition, that is the MPx, MPy is equal to MP for column A is equal to M0, and MPb and MPd they are equal, that is equal to 1.5 M0, and MPc is twice M0. So, since the moments are in this proportion, and therefore, the yield shears also can be obtained in that particular proportion. So, we know for all the columns the yield shear, And once we know that, then we go ahead with the calculation, that is the values of ux, uy and u theta are given in these at kth time station. This is the velocity, this is the acceleration. The fk, that is the vx, vy and v theta is given, that is at the center of mass, the total shear in the x direction, total shear in the y direction, and the rotational shear or rotational moment, that is given as this at the kth time station. The individual shears in different columns in the x and y directions are given like this, and this is the incremental ground acceleration at given for that particular delta t. Now, the forces in the columns that are pulled back later, but in the beginning we compute the value, the Ki matrix, and once we obtain the value of the Ki matrix, then using that Ki matrix one can check, find out the solution for the problem, and we see that for each one of the columns the phi value is less than equal to 1. Therefore, Kt is simply is equal to Ke, that is the correction term Ke minus Kp, that correction term Kp does not come into picture. So, that is the initial state of the system. Now, for that initial state of the system, we compute the value of K bar, and with the help of this K bar and delta P, we get the value of delta U, that is delta U is equal to K bar inverse delta P, and we find out the value of delta F, that is Kt into delta U, and we get the value of Uk plus 1, that is the next time step, the values of the 3 displacement, that is the 2 displacement in the x and y direction and a rotation. The Fk plus 1 that we obtain, that is the total shear in the x and y direction and the rotational force over here, that we obtain at the end of the time step, and the shear forces in each one of the columns are calculated, they are shown over here, and then we check for the yield condition by utilizing this equation, and we find that for column A, B, C and D, for all the columns the yield condition is violated, that is it has become more than 1. So, therefore, the forces are to be pulled back so that the yield condition is satisfied. So, for that we calculate the EA, EB, ED and EC as this one, that is 1 by phi A square root of that, 1 by phi B square root of that, and so on. And with the help of these factors, now we go to these values, that is the delta UE is calculated, and the value of E bar is calculated as 0.83 for all the columns, where E bar x is given by this. Then delta P2 is calculated, that as 1 minus E bar into delta P. So, we get the value of delta P. Then we calculate Ex and Ey for the new state of stresses in the column. Then from there we get the values of Hxi and Hyi, for each one of the column because we know the revised value of the shear and the yield shear. From that ratio one can calculate these H values. Then one can calculate the values of Bxi and Byi, and once they are and then we calculate the Gi value for all the columns. And after we have obtained that, then the components of the Kp matrix, that is calculated using this formula, and the components of the Kp matrix are given over here, and then one calculates the Kpx, Kpy, Kp theta, so that the modified tangent stiffness matrix that comes out to be is equal to Kt is equal to Ke minus Kp. We know all the elements of the Kp matrix now, and that is how we get the value of the Kt matrix. And once we get the value of Kt matrix, then from there we get the value of K bar, and using the value of K bar we can get delta U2, that is the part of the displacement which is the plastic component of the displacement, and from there we can find out delta Upxi and delta Uppyy for all the columns, and find out finally the total displacement at the center of mass, that is by summing of the scaled displacement delta U1 and the plastic displacement part incremental displacement delta U2, and delta VBPI for each one of the elements can be obtained, and from this delta Upxi multiplied by the corresponding modified stiffness matrix. In that you can see that the both Ke and Kp, they are present, the elements of Ke and Kp are present. And finally using them we get the shear values, new shear values in the columns, and once we get the new shear values of the columns, then we apply this yield criteria and check whether the yield condition is violated or not. And for this particular problem it is found that once we make this particular modification, then the phi value for columns A, B, C, D, they remain more or less equal to 1, that is no further iteration is required. So what has been done over here is that in the beginning we have obtained the values of the shear at different columns and checked that the columns were not yielded or have not yielded. So therefore everything was in the elastic state. So using now Kt matrix which does not have any Kp component, we obtained the value of delta U, that is the displacement at the center of mass, and added that displacement with the displacement at the beginning of the time step to find out the total displacement, and then we found out the revised shear forces in each one of the columns in x and y directions. And then we checked the yield condition, we found that the yield conditions were violated, and therefore the forces in the columns were pulled back so that the yield condition is satisfied, that is phi becomes equal to unity. So with the help of that we found out a revised value of the displacement delta U1 and delta U2, that is the two components, plastic component and the elastic component of the displacements, and finally get a revised value of delta U, and that when we added with the previous displacement, we found that the yield conditions for each one of the columns were satisfied, therefore, no further iteration was required.